Hello everyone, in this video I'm going to solve a chemistry assessment exam that students recently took who were preparing for NEET exam or IIT exam and even for the MCAT exam. So I'm going to talk about how you approach solving these problems. A lot of time in these entrance exams you are up against the clock, so you want to make sure you use your time efficiently and you think through the questions efficiently as well. So let's start out with this question 1 here. So this question says, which of the following gives the correct number of subatomic particles in sulfur 2 minus 34? So obviously we're dealing with sulfur here, and you wanna, if you can go back and check in the periodic table, the atomic number for sulfur is 16. So that means it's got to have 16 protons in there. And then we have 34 as its mass number, so that means the number of neutrons would be 34 minus 16, so that's going to give you 18. And then as far as the electrons go, so if this was neutral, the number of protons and electrons would be the same, but since it's not neutral and it's got a 2 minus charge on it, the number of electrons would be 2 more than the number of protons, so we can have 18 electrons in there. So your answer in this particular case is going to match with this answer option D, where we have 18 electrons, 16 protons, and 18 neutrons as well. Okay, let's look at this next one here. It's asking for how many electrons can be placed in atomic orbital or orbitals with n equals 4 and m of l equals +1. So obviously this is your shell, and m of l is going to be your orbital. So we have to figure out how many possible orbitals you can have with this particular value of +1 when the n is 4. And if you recall the magnetic quantum number, which gives you the number of orbitals, is actually dependent on your angular quantum number, which is the value of L. But then the value of L is actually dependent on the value of N. So if your N is 4, then your possible L values would be 0, 1, 2, and 3. So then your possible M of L values would be 0 when L is equal to 0. And when L is 1, your possible M of L values would be +1, 0, and -1. And when your L is 2, then we're looking at -2, -1, 0, +1, +2. And then I can do something similar when L is 3. So I'm going from -3, -2, -1, 0, and then +1, +2, +3. Now if I look how many values of +1 I get for M of L, I would have one of them is right there, another one is right there, and you have another one right there. So you technically get 3 values of +1 for this particular value for n equals 4. So each orbital contains a max of 2 electrons, so that means I'm going to have a total of 6 electrons for this particular example here. So the answer is actually going to be it's going to be 6 electrons. If you pick 2 electrons, that's not going to be correct. It has to be a 6 electrons. That's how you really want to break it down. Let's look at this number 3. Which of the following atoms or ions have exactly 2 unpaired atomic orbitals? So when we're talking about atomic orbitals and how many of them are paired or unpaired, we are actually going to be looking at your electronic configurations. And all these guys here, where you have chromium and manganese 2+, titanium 2+, and copper and vanadium 1+, they're all actually in the third, or you can say in the fourth row, or all of those are going to be in the 3D here. So maybe I can write down the shorthand electronic configuration for these guys. So the argon is going to be the nearest noble gas to that. So then I can come down here. So for chromium, it's going to be argon, and then I'm going to remove, it's going to have 1 electron deficiency, so I'm going to remove the electron from 4s. So don't remove the electron from the 3D. Like if I just draw the chromium by itself, its electronic configuration is 4s1 and 3d5. Now, when it comes down to removing the electrons, you always remove the electrons from the highest n value. So your highest n value here is actually going to be the 4. So I want to remove the electron from here first. So when I do so, I'm going to be getting argon and then 3d5. So this D subshell here, that's going to have 5 orbitals, and each one of those are going to be half filled. So it's not really going to have exactly 2 unpaired orbitals, but rather this will give you 5 unpaired orbitals. So that's not the answer we're obviously looking for. We can check manganese 2 plus, and manganese 2 plus atomic number is 25. So when I draw, maybe I can just do argon, and it would have been 4s2 3d5. But since I want to draw manganese 2 plus, so I'm going to take out 2 electrons. So when I take out 2 electrons, I'm going to be taking out from the 4s again. So that's going to be 3d5. So it's going to give you 5 unpaired orbitals again. So that's not really going to be the answer either. Let's look at titanium. Titanium is 22, so it's going to be argon 4s2 and 3d2. And when I go ahead and take out the electrons from 2 electrons from titanium, I'm going to be removing the electrons from the 4s again. So it's going to be argon and 3d2. So now that looks very promising. Now you got 2 electrons in the 3d, so that means both of those orbitals in that 3 are going to be unpaired. So that's what they were really asking for. Now, before you make your decision, let's just kind of look through all of these guys here. Um, so then coming down to copper, well, it doesn't really have any charge on here, so it's just going to be argon, and copper is 29 in the periodic table. And remember, it does have an exceptional electronic configuration where it's going to be 4s1 and 3d10. So it actually gives you only one unpaired orbital that's going to be coming from in a 4s. We're actually looking for 2. Let's check the vanadium. Vanadium's atomic number is 23. So I'm gonna have argon. Well, let me just draw the one without the charge first. So argon, and it's gonna be 4s2, 3d3. So that's vanadium. And when you do 1 plus, I'm gonna be removing 1 electrons from the 4s. So it's gonna be 4s1, 3d3. So it's actually going to have 1 unpaired from the 4s and 3 unpaired from the 3d. So it's going to have a total of 4. So it's not going to be the answer either. So that leaves you with the titanium being your answer for this particular question here. Okay, let's move on to this next one. It's asking for how many moles of magnesium phosphates can be produced if 3 moles of magnesium chlorides are reacted with 4 moles of sodium phosphate. And you are given an unbalanced equation. If you're given an unbalanced equation, the first thing you want to do is make sure you balance it. So when I balance this equation, there's really not any particular rule on balancing. It's just a couple of tricks that you can always use. And if um, if it works out, that's fine. If it doesn't work out, you try something else. And I always tell students to focus on the element that has the highest subscript first. So maybe like sodium 3 here and magnesium 3 here. Maybe try to balance those out. And the other rule you want to know, or other trick I would say you want to make sure you follow is balance the element that's by itself at the very end. So obviously we don't really have any element or any molecule here that's by itself. So we would have to balance, we would have to start out with maybe sodium and magnesium balancing first. So let's start out with magnesium for a minute. So if I have 3 magnesiums on the product side here, and to make 3 magnesiums on the reactant side, I would have to put 3 here. All right, so that, and then the next thing I want to do is maybe once I put 3 magnesiums here, it gives me 6 chlorines on the on the left side, on the reactant side. So I want to make sure I have 6 chlorines on the product side. And so far, there's only 1 chlorine in NaCl, so that means I can go ahead and put 6 there, and then C, that takes care of the chlorine. But now what really happens to the sodium? Let's talk about that. So in sodium, I have 3 sodiums on the reactant side, but when I look at it on the product side, I got 6 sodiums. So to make 6 sodiums on the reactant side, I would have to multiply this by 2. So that takes care of the sodiums as well. That leaves you with the phosphate. So let's check the phosphates here. So, or you can say the phosphorus and the oxygens alone. So you have 2 phosphorus here on the reactant side. You do have 2 phosphorus on the product side as well, so that's fine. Let's look at the oxygens. You got 8 oxygens on the reactant side. You do have 8 oxygens on the product. So that seems to be working fine as well. So that means at the end of the day, you're just going to have 1 in front of this magnesium phosphate. If it's 1, you don't necessarily have to write it. Now, the second part of this question is asking like how many moles of this magnesium phosphate would be really made if I'm using 3 moles of magnesium chloride. So when I'm trying to look for the relation here, I can clearly see that the relation between the magnesium chloride and the magnesium phosphate is 3 to 1. So for every 3 moles of magnesium phosphate, magnesium chloride, I'm making 1 mole of magnesium phosphate. And the question does tell you you do start out with the 3 moles of magnesium chloride here. So that means based on the magnesium chloride, I would be making only 1 mole of magnesium phosphate. Now, since you have 2 reactants, I don't know which one of them is going to be the limiting reactant, so I got to check I got to do the same thing for the second guy. So sodium phosphate, when I try to relate that, it's a 1 to 2, 2 to 1 mole ratio. Another way of saying for every 2 moles of sodium phosphate, I'm making 1 mole of magnesium phosphate. Now, the question tells us that we're starting with 4 moles of magnesium sodium phosphate. So if we were doing for every 2 moles, we're making 1 mole of magnesium phosphate. So that means for every 4 moles of sodium phosphate, I should be making 2 moles of magnesium phosphate. You can always write it like this. You have 4 moles of sodium phosphate to start out with. And our balanced equation tells us that for every 3 moles, or rather for every 2 moles of sodium phosphate, I'm making 1 mole of magnesium phosphate. So however you want to do the math here, but make sure you can do this as quickly as possible. I'm sure I'm taking a little bit of time here, but just trying to explain it to you guys. But if you can do it quickly in your head, that's going to be even better. So that gives you 2 moles of magnesium phosphate from this scenario. But think of this way, by the time you have used up your 3 moles of magnesium chloride, you would not have any of the magnesium chloride, so that is actually going to be your limiting reactant. And you always make the product based on the limiting reactant. So at the end of the day, it should be only making 1 mole of magnesium phosphate for this particular reaction. Let's try this next one here. It's asking to arrange the following atoms or ions in increasing order of their size. The very first thing you want to look for is what group or what periods rather they are all in. So when I'm looking at calcium, calcium is actually going to be in the fourth shell or in the fourth period. Argon is in the third, so I'll say 3 here. Calcium 2 plus, even though it's in the fourth, but remember it's in the 2 plus, so it actually loses its valence electron. So now it falls back to the third shell. So that's something you want to make sure and you know. Sulfur, sulfur 2 minus, they're all going to be in the third shell together. Potassium again is going to be in the fourth shell, and then potassium 1 plus is kind of similar story. It's going to fall to the third shell because it loses its valence electrons. So first of all, whoever is actually in the fourth shell gotta be the biggest one. So we have 2 atoms that are in the fourth shell, which is going to be the calcium and the potassium. Now between the calcium and potassium, who's going to be really bigger? And when I see the relation between those two, you can kind of see that they're in the same period. And as you go to the right on the period, your size drops. So between the calcium and the potassium, your potassium is actually going to be greater in size than the calcium. So I should have potassium being the biggest, followed by the calcium. So then you can kind of start eliminating some of your answer options. Like, I can get rid of this A, maybe I can get rid of this B as well, and then that leaves you with C, D, and E, and then you're gonna have to do some other work here to figure out what the order really gonna be here. Now, when I'm looking at the rest of these guys, the cations are usually smaller because when you're looking at the cations, you're gonna have more protons and they're gonna have less electrons that you're really working out with. But when I'm looking at the sulfur, sulfur 2 minus, so let's just focus on maybe sulfur and argon for a minute because they don't have a charge and they are going to be in the same period. And number 3, argon is indeed more onto the right side and sulfur is more onto the left side. So sulfur is actually going to be bigger than the argon. So I can say sulfur is going to be greater in size than the argon. And then you can kind of look in the answer options here and which one you have sulfur being bigger. Well, we do have sulfur bigger here. Okay, so that's fine. And then what else? We do have, well, sulfur bigger in here as well, and sulfur bigger in here as well. So that doesn't really help. Maybe let's check the size difference between the sulfur and sulfur 2 minus. Now, the anions are always going to be bigger than their parent atoms because in case of sulfur 2 minus, you are have only 16 protons and you're taking care of 18 electrons. So since you have more electrons outside, it's going to be more chaotic. It's going to be hard for those 16 protons to take care of those 18 electrons. So that means your sulfur is going to be smaller than your sulfur 2 minus. Now let's check which one of those really follow that. This one follows that, okay? This one does not follow that, so that you can take out E, and then the other one also follows this, all right? So that leaves you down with between C and D. And then at the end of the day now, it's really between the calcium 2 plus and the potassium. Now between those two, in case of calcium 2 plus, you have 20 protons and 18 electrons. And then in case of potassium, you have 19 protons and 18 electrons. Now, in case of calcium, you have more protons to take care of less electrons that are outside the nucleus. So they're going to have a better control on those 18 electrons. So that's going to shrink the size of this calcium ion here. So the calcium 2 plus actually should be smaller than the potassium plus. So that leaves you with your answer option D there. That's the only thing you really got left out with. So that's how you're really going to break down. Obviously, you need to know your trend for your atomic size and also for your ions, whether is you comparing the cations with an apparent atom or you comparing the anion with the parent atom as well. Let's try this next one. It's asking to predict the identity of the third shell element. So when we say third shell, we're talking about third period in the periodic table based on those hypothetical ionization energies. So remember, the ionization energies are usually our endothermic values because you're going to have to put in some energy to remove an electron. And typically, your successive ionization energies goes up. So if I want to look at the trend here, I can clearly see that, okay, well, starting from IE1, I have, 578. Hypothetically, the next one is 1817. So it is going up as we have expected. Your next ionization energy went up again. So that's after losing the 3 electron. And then when we look at IE4, there isn't a great amount of jump from the IE3 to IE4. So we have 2745 is in our IE3, but your ionization energies 4 is close to 12,000. So that's a significant difference in their energy. So what does that technically means that after losing 3 electrons, it doesn't really want to lose the 4th electron because maybe after losing the 3 electrons, it has gotten into the valence, it has gotten into the stable electronic configuration, and that would happen only if you lose all your valence electrons. So this tells you that you should have 3 valence electrons, and then you go back in the periodic table and check in your third period Which one has three valence electrons? So that comes down to your aluminum. Aluminum has three valence electrons, so that is going to be your answer here. Let's try this next one. It's asking for which one of them is not a redox reaction. So before you actually do this question, you have to know what a redox reaction is. And a redox reaction is where you have a reduction and oxidation being taking place at the same time. And um, to really figure out whether you have an oxidation or reduction going on, you can do so with the help of your oxidation numbers. So in every single one of those, you're going to have to actually figure out, is there any reaction here that does not have the oxidation number of its elements changing? So let's start out with A. So carbon by itself, it's going to be 0, and oxygen, when it's in natural form, that's also going to be 0. When it makes carbon dioxide, so remember your oxygen is mostly 2 minus or minus 2 here. So that's going to give carbon to be plus 4 because remember you have two oxygens, so that's going to be minus 4. So to balance out minus 4, carbon must be plus 4. So you can clearly see the oxidation numbers are changing. So this one would be in a redox, all right? So we're looking for something that's not going to be redox. So let's try the next one here. H2O2, that's a peroxide. Your hydrogens, when is bonded with a nonmetal, it's always going to be plus 1. So this is going to be plus 1. So that means your oxygen here, since you have two hydrogens, that's going to give you a total of 2 plus. So that you must have a 2 minus coming from your oxygen. So since you have two oxygens, each oxygen must be carrying a minus 1 oxidation number here. Um, Remember I said earlier the oxygen is mostly 2 minus, but it's in case of peroxide when it's minus 1, in case of superoxide it's going to be minus half. Now, let's look at your products. In case of products, we can see that your hydrogen is still going to be plus 1 because it's bonded with a nonmetal, but then your oxygen all of a sudden in water is actually going to be minus 2, and oxygen when it's by itself here, it's going to be 0. So you are changing the oxidation number of oxygen from minus 1 to minus 2 and to 0. So this is a reaction where it's the same element that's undergoing oxidation or reduction, and these are called disproportionation reaction. So that is also going to be a redox reaction. Let's check out the next one, ammonia. So in case of ammonia, hydrogen is still bonded with a nonmetal, so that's going to be plus 1. So that's going to give nitrogen to be minus 3 here, because you have three hydrogens. When it's nitrogen by itself, that's going to be 0. That's in natural state. Hydrogen by itself, that's also going to be 0. So you are indeed changing the oxidation numbers here. So you are dealing with a redox reaction here. When you look at D, zinc by itself is going to be 0. Copper sulfate. Sulfate is usually 2 minus altogether, if I want to look at it that way. That means copper is 2 plus here. And copper here is going to be 0. And your zinc now is going to be plus 2. And sulfate still stays as in a 2 minus altogether. So you're changing the oxidation number of copper and zinc here. So that's also going to be in a redox. This last one we have calcium carbonate. So in calcium carbonate, remember your carbonates are actually um, 2 minus altogether. That's because your calcium is 2 plus. But if I want to look at it individually, I can do so as well. Your oxygens is going to be minus 2, but since you have three of those, that's going to be minus 6. So that means your carbon must be plus 4 here to balance out the minus 6 because you have a 2 plus coming from the calcium. Now in calcium oxide, you're going to have calcium to be still 2 plus and oxygen still to be 2 minus. So we're not really changing the oxidation number of calcium and oxygen so far. Let's look at the next one here. The oxygen here is still going to be 2 minus, so that's going to give you a total of minus 4. So that means your carbon must be plus 4. So in this particular case, you're not changing the oxidation number of any of these elements in the reaction. So this is not going to be a redox reaction. Now this next one is asking for the most polar bond, and the polarity typically has to do with electronegativity values, and you don't really have to memorize the electronegativity values, but just remember As you move to the right side of the periodic table, your electronegativity increases, and as you go down, it decreases. So when I'm looking at these bonds that I'm comparing here, we have an NH, so you know the hydrogen is way onto the left side of the periodic table. Nitrogen is on the right side. We have a carbon's H, hydrogen, hydrogen. That's going to be relatively nonpolar because that's the bond between the same type of atoms here. And then you have the HF and the OH. Now, if you look at really the difference, every single one of those has hydrogen involved, but you have nitrogen, you got a carbon, you got a fluorine, and you got an oxygen here. Now, out of those four elements, your fluorine is going to be the most electronegative, and fluorine is indeed the most electronegative element. And keeping the other element to be the same, that means the HF is indeed going to be the most polar because they're going to have the most electronegativity difference between the hydrogen and the fluorine. So that leaves you with this answer here. Okay, which of the following equations represents the second electron affinity of an oxygen atom? Remember, your electron affinity is when an electron is added to the gaseous atom. So when it does the first electron affinity, so that would have been oxygen as in a gas gaining one electron, and you're making an oxygen 1 minus in the gas form. Now, when you do the second electron affinity, we would have to start out with oxygen 1 minus gas, and I'm adding the second electron now, and that gives you an O2 minus. So that actually matches with this answer option D here. So just kind of knowledge-based question here. Number 10, active ingredient in gasoline, so now also called petrol, is octane that has a formula of C8H18. Octane burns inside internal combustion engine in the presence of oxygen gas to produce carbon dioxide and water. What would be the coefficient of oxygen gas when you balance this equation? Well, you're not really given an unbalanced equation, but you're kind of given a hint what you are really doing and what you're really going to be making at the end of the day. So you are starting out with C8H18 and you're burning this in the presence of an oxygen. So I'm going to go ahead and react that with an oxygen, and it tells you you're making carbon dioxide, so CO2, and water. So based on that, those are the only products you have, and those are the only reactants you have. So you gotta balance this equation. And what I have said earlier, that you want to start out with maybe the highest subscripts first. So maybe when I looking at this hydrogen here, we got 18 hydrogens here. And you also have an oxygen here that's by itself. And I did mention that earlier that you want to balance the atom that's by itself at the very end. So first worry about balancing this hydrogen here. So hydrogen, since I have 18 on the reactant side, to make 18 on the product side, momentarily I can go ahead and put 9 here. Now I want to go ahead and balance your carbons as well. So you have 8 carbons on the reaction side. To get 8 carbons on the product side, I would add 8 here. And then I'll worry about how many oxygens I really got. So I got 8 times 2, that's 16 oxygens here. 9 oxygens coming from water. So 16 plus 9, that's going to be 25 oxygens. We need to have 25 oxygens on the reactant side. And to get 25 oxygen on the reactant side, maybe I can momentarily put 12 and a half in there. But you can't really have fractions and decimals in your balanced equations. So what can you do to make this a an integer? So to make this integer, I can multiply this whole reaction by 2. So when I multiply this whole reaction by 2, I would have 2 here, I would have 25 here, I would have 16 here, I would have 18 here. So that is actually going to be your coefficients when you balance this equation. So all other ones gets canceled out. So I can probably just get rid of these. So the question was asking what's going to be the coefficients for the oxygen gas. So that's 25. So it's going to be answer option B there. Let's look at this next one. Draw the Lewis-Strauss structure of CCl4 and select the correct statement. Select all that apply. Um, So first of all, figure out what's going to be the loose dot structure for CCl4. So when you're drawing CCl4, the total valence electrons is going to be carbon has 4, and you have 7 on each chlorine, so that's going to be 28 plus 4, a total of 32. So you must be using 32 altogether. And if I just want to draw it two-dimensionally first, I would put carbon in the center, and I would have one bond between the chlorine and the central atom. So that uses up 8 electrons, because remember each bond brings in 2 electrons. So that uses up 8 electrons, so that leaves you with 24. And now I want to complete the octets of the surroundings first. So every chlorine should have 6 electrons here. So that would take care of their octets. And when I do so, I uses up the remaining 24 electrons. So that means I have used up all 32 electrons here. So this actually gives you a very um, symmetrical structure where the left and the top and the right and bottom, they're all kind of symmetrical to one another. If I want to draw that in the form of three dimension, I can have two bonds in the plane like this, and then I can have one bond coming out of the page, because that's how you typically draw the tetrahedral, and one bond is going to be going back in the page. So let's look at these questions here. The compound has a tetrahedral electronic geometry here, and a trigonal planar molecular geometry. Now, when we're looking at around the central atom here, there is 4 electron domains, and all those electron domains are coming from the bonding domains. So there's no lone pair on the central atom. So when there's no lone pair on the central atom, your electronic geometry and your shape is actually going to be the same. So that means A cannot be the correct answer there. Let's look at B. Overall molecule is polar because it contains polar bond and having a net dipole moment. Now let's look at the polarity of the bonds first. When I'm looking at carbon chlorine, chlorine is more electronegative than the carbon. So I can certainly write down that each of these chlorines is going to be partial negatives, and your carbon is going to be partial positive. And when I'm drawing these dipoles, we'll have dipoles going from the positive to the negatives. And I can certainly just do that on the two dimension, but if you want to do that on the three dimension, that's fine as well. But when I do that on the two dimension, you can clearly see all these dipoles actually cancel one another out. The left one cancels the right one, the top one cancels the bottom one. And that would have been the same story technically in the three dimension. It's just hard to see in the three dimension when you're drawing it on the page here. So even though it does have polar bonds, but overall molecule is actually going to be nonpolar because there is no dipole moment. All those dipoles cancel one another out. So this is going to be incorrect as well. The C says overall molecule is nonpolar because it contains nonpolar bonds. Well, it does have polar bonds, so that makes this incorrect as well. Let's look at D. Overall molecule is nonpolar because it contains polar bonds. Okay, so far so good. And have no net dipole moment. So that actually works out well because we do have polar bonds here, but at the end of the day, there's no net dipole moment, and because of that, it's overall nonpolar. Let's look at E. The compound has tetrahedral electronic geometry and molecular geometry. Well, it's got 4 legs on here, so electron domains of 4 gives you a tetrahedral electronic geometry and tetrahedral molecular shape as long as there is no lone pair on the central atom. So that would also be correct. That's why I say select all that applies. So D and E are going to be the correct answers for this one. Says the student mixes 20 milliliters of 0.5 molar acetic acid and 12 milliliters of 0.5 molar NaOH, and what is going to be the approximate pH of resulting solution if the pKa of acetic acid is 4.7. Now, it may look a little bit complicated, but there is really not a lot of math going on with this question. You have to know what your half equivalence points and your equivalence points are technically for this question, and also have to know that this is a monoprotic acid, um, and this is a monobasic base. So when you write down the equation between those two, it's actually going to be a 1-to-1 mole ratio. So I can certainly, if I want to write down the equation, and you don't necessarily have to write it in the exam because you want to save up some time. Um, but when I do so, I'm getting CH3COO minus Na plus and water. So this is a 1-to-1 mole ratio. Everything is balanced already. So I really got to figure out how many moles I really have here. So when I'm looking at the moles for your acetic acid, so I'm looking at 20 milliliters of 0.5 molar. So 20 milliliters is going to be 0.02 liters. So 0.02 times 5, when you multiply that out, it's going to give you 0.01 moles for the acetic acid. We'll do something similar for the NaOH, so have 0.012 liters. So when I multiply 0.012 liters by zero point 0.5 to get the moles, I'm getting 12 times 6 is 60. 12 times 5 is 60, so that's going to be 0.006 moles. So you have a total of 0.01 moles of your acid, and you are have a moles of 0.006 for your base. So you're neutralizing not half, but a little bit more than half of your acid, because half of the acid moles is going to be 0.005. So you're certainly neutralizing a little bit more of the half of your acid. So that means you're not really going to be exactly at an half equivalence point, but you're going to be a little bit over half equivalence point. And you can make a nice table if you want. So I'm just going to do that right here. So I'm starting out with 0.01 moles here, and I have 0.006 moles here. Initially, I don't have those. And then when I look at the limiting reactant, it's going to be 0.006. So I lose 0.006 here, and I make 0.006 here. Now, if you can do this math in your head, that's great, so that you can save a lot of time. But if you cannot, you want to go ahead and still do it so that you can get the question right instead of spending a time on it and not getting it right at the end of the day. So there is your weak acid here and its conjugate base. So you have both of those in there. That makes it a buffer solution, and you can certainly use the Henderson-Hasselbalch equation, which is pH equals pKa plus log of your conjugate base, which is CH3COO minus, divided by CH3COOH. So then when I solving this, your pKa is 4.7, and that's going to be log. Your base moles are 0.006. Remember, you can use moles here. You don't have to have the concentrations for these guys when you're using Henderson-Hasselbalch equation, and this is going to be 0.004 rather. So 0.004. Now you don't really have to do the rest of the math. So think of this: you have a higher number in the numerator and a lower number in the denominator. So log of that, this is going to be greater than 1. So log 1 or greater than 1 is actually going to be a positive number. So you're going to be adding something to the 4.7. So the answer has to be greater than 4.7. So that rules out A, that rules out C, and that rules out E. So that leaves you with B and D. But remember, this is still in a buffer solution. Your buffer solution stays within plus and minus 1 range of your pKa, which is 4.7. So you can still have in a buffer system between 3.7 to 5.7. So your answer must be between those two, technically. So that leaves you with 4.9 here. So that's how you really want to tackle this question. Let's look at number 13. So I'm probably just consider the following compounds and select the correct statement. You got this ethanol here. So you got a lot of nonpolars on the left side. OH, that's going to make hydrogen bonds. The CH3, that's just nonpolar. CH3O, CH3, you do have an oxygen carbon bond there, so that is going to be polar. But let's just look at the statements here. So all three compounds can make dispersion forces. So regardless what compound you're really dealing with, all of them can make dispersion forces. So that's true. Compound 1 and 3 can make hydrogen bonds. Well, we did say that one can make hydrogen bond because you have the hydrogen directly connected with the oxygen. Let's look at 3. Even though it kind of seems like the hydrogen is next to the oxygen, but that's not really true. When you draw its Lewis-Strauss structure, you're actually going to have the hydrogens connected with the carbons here, on either side of the oxygen. So oxygen does not really have any hydrogen directly connected with it, so it's not going to be able to make hydrogen bonds. So B is incorrect. Compound 1 can make hydrogen bond and dipole-dipole interactions. Well, that's true. It can make hydrogen bonds and it can also make dipole-dipole interactions because when you look at its Lewis-Strauss structure, you do have that carbon-oxygen bond that is going to be relatively polar. So since we have polar bonds, molecule is polar. There's no internal plane of symmetry, so that is going to be able to make dipole-dipole interactions as well. So C is correct. Compound 1 will have lowest boiling point and highest vapor pressure. So remember, whoever actually has the strongest intermolecular forces should have the highest boiling point because they correlate with one another. So since out of those three molecules, and they have relatively similar size, if not the same, then I want to look at the type of intermolecular forces being made. So on the one, I have all three. On two, it's only dispersion. And on three, you have dipole, dipole, and dispersion. So based on that, one should have the highest boiling point, and that would also give you the lowest vapor pressure. But that's D saying that otherwise, so that's not going to be correct. Let's look at E. Compound 1 has the highest boiling point, so that's good. Compound 2 has the highest vapor pressure, so let's just double check that. So compound 2, we said it's only making dispersion forces, so it's going to have lowest boiling point. So if your boiling point is the lowest, its vapor pressure is going to be the highest. So remember, it it's an inverse relation between the boiling point and the vapor pressure. So that has to be correct as well. So that leaves you with your answer A, C, and E in there. Consider the following phase changing. Select the correct statement. You're making solid to liquid to gas. The conversion of the compound from solid to liquid is exothermic. Well, when you're going from a solid to liquid, that's actually an endothermic process because you need energy to break down those lattice interactions. Think of ice converting into the liquid. When the ice convert into the liquid, it's not going to convert on its own. You have to have a relatively warmer temperature for the ice to melt. Otherwise, it's not really going to melt. So that's an endothermic process. So that's A is incorrect. The conversion of a compound from a gas to liquid is vaporization. Well, that's actually called condensation. The vaporization is the other way around. The vaporization when the liquid goes to the gas, and it is exothermic, but it's not really vaporization, but rather it's called condensation. The process of water, the conversion of water to ice is an exothermic. Um, that's true. When you go from liquid back to the solid, it's an exothermic process and it's called melting. Well, it's not really called melting, but rather it's called freezing. The melting would be when you're actually coming from the solid to a liquid. So that's incorrect as well. The conversion of vapor to water is an endothermic. Well, that's going from the gas. So, when you're going backward, it's not an endothermic, but rather it's an exothermic process. So that's incorrect as well. So that leaves you with the last one. Let's just check that. The direct conversion of solid to a gas is an endothermic, which makes sense. We said when you're going from solid to liquid to gas, going that way is always going to be endothermic. And it's called sublimation. It is called sublimation when you're subliming solid directly to the gas. Take an example of dry ice, which is solid carbon dioxide. When you leave solid carbon dioxide in the air, it just sublimes into the gaseous carbon dioxide. Okay, which of the statement is correct about the position of the elements in the periodic table? Well, this is where you have to know your periodic table, know you don't have to memorize it, but just make sure you know where your alkali metals are, where your transition metals are, where your noble gases, your halogens are, and all those things. So hydrogen is an alkali metal, and the first one it says, well, hydrogen is not really a metal, so that rules it out. So you don't have to look at the rest of the things. Neon is a noble gas. That is true. Neon is in the last group in the periodic table. That's fine. Bromine is a halogen. That's also fine. And francium is an alkali metal. That's also fine. Francium is the last element of the first group, which is the alkali metals. So that's fine so far. Let's look at the other ones as well. Silicon is a metalloid. That's fine. Hydrogen is not a metal. That's fine. Fr is an alkaline earth metal. Alkaline earth metals are the group 2 metals. So remember your Fr is actually in the group 1 metal. So that's not going to be the correct answer. Zinc is a transition metal. Yes, it is in the D block. Hydrogen is metal. Well, that's an incorrect. Now we just said that. Hydrogen is non-metal. Carbon is a metal. No, carbon is a non-metal. So that rules out that as well. So that leaves you with the B there. Let's look at 16. What disturbance would shift the following equilibrium to the right? So we're given this reaction, we're given the delta H, that's going to be -92. So that is a exothermic process. So make sure you are aware of that going forward. So when you're adding NH3, so we're adding the product, that means it's going to shift the equilibrium to the left. So what we're really looking for, what would disturb the equilibrium to the right side? So that's not going to be the answer. Let's look at B, removing hydrogen. So if you remove the reactant, it will again shift the equilibrium backward to the reactant side. So that's not going to be the answer either. Increasing temperature. If you increase temperature, it favors endothermic process. So you're going forward, giving you delta H of -92, that's exothermic. So that means reverse reaction is endothermic. So when you're increasing the temperature, it's going to favor the reverse reaction. So we're not looking the reverse reaction, we're looking the forward reactions. Increasing volume. If you increase the volume, you are decreasing the pressure. So when you decrease the pressure, it typically shifts to the side that has more gas moles. And in this case, you have more gas moles on the reactant side. You got 3 from the hydrogen, 1 from the nitrogen, so that's 4. And on the reactant, on the product side, you only have 2 gas moles. So this is actually going to be shifting to the left side again. That leaves you with the last one, increasing pressure. So when you increase the pressure, that shifts to the side. Remember IPL. Increased pressure shifts to the side that has less gas moles. So less gas moles are going to be on your product side here because we have only 2. So that's going to be the only answer there. Which of the following contains strong electrolytes only? When we're looking at strong electrolytes, the strong electrolytes are usually the salts that are going to be soluble in water. And the other chemicals that we're going to be looking at, they are strong acids and bases that are going to be strong electrolytes. So that's what you really have to figure out in this particular case. NaCl does dissolve in water. We all know that. Table salts dissolve in water. HCl is one of your strong acids, so that would dissolve in water as well. So this should be your answer, but let's just check the other guys as well. NH3 is not a strong base. It's a weak base, so it's not going to be completely ionized into the water. H2SO4, H2SO3 is not a strong acid. Remember, that's not a sulfuric acid, that's a sulfurous acid. So since it's a weaker acid, it's a weak electrolyte. It ionizes partially. Calcium carbonate, on the other hand, in case of this here, it should have been D here. The calcium carbonate in this case is an insoluble salt, so that's not going to be a strong electrolyte either. NH4, NO3, the ammonium nitrate does dissolve in water. That's in a strong electrolyte, but HF is in a weak acid, so that's not going to be in a strong electrolyte. So that leaves you with an answer option A there. A student mixes 10 grams of NaOH in enough water to make 100 milliliters of solution. The resulting solution has a density of 1.1. The molality of resulting solution will be less, more, equal than the molarity. Well, you're probably going to have to figure out the molality and the molarity here. Now, the numbers are actually placed in a sense, or the numbers are actually provided to you in a sense that you can do this math in your head. You don't really need to have a calculator. So first of all, to find the molarity, I would have to have moles over the volume, so moles over liters, right? So moles for NaOH here, so I have 10 grams, and I can divide that by molar mass. So 1 mole of NaOH, figure out the molar mass of NaOH. So sodium is about 23, oxygen is 16, that's 39, and hydrogen is 1, so that's 40. So it's going to be 40 grams. So 10 over 40 is how much? It's 1/4, so that's going to be 0.25. moles. So I can do 0.25 moles here, divide that by the volume of solution, which is 100 milliliters. We need to change that to liters, so that's going to be zero point 0.1 liters, so zero point 0.1. So that's going to give you 2.5 molar. So that's going to be your molarity. Now I can figure out the molality as well. So remember the definition of molality is you have moles over kilograms of your solvent. So you got to figure out how much solvent you have. You still have the moles. In order to figure out the solvent, maybe I need to figure out the mass of your solution. So I'm starting out with 100 milliliters of solution, and we're told the density of solution is 1.1 grams per milliliters. So that gives you 110 grams of your total solution. But remember, out of that, 10 grams is coming from NaOH, so minus 10. So that leaves you with 100 grams of your solvent, which is going to be the water. So that comes down to 0.25 here divided by the kilograms of solvent is still going to be 100. So it's going to be zero point 0.1 kilograms. So that is still going to be 2.5. So the molality and the molarity comes out to be the same because just numbers falls right into those positions where they're equal one another. So this is going to be C here. The structure of aspirin, also called Dispirin, is a trade name, is shown below. Which of the following function group is not present? So you have to know your function groups in this particular case. Before you're looking at the answer options, it's probably just better to look at what function groups you got there. This is going to be your ester. You do have an aromatic here. And this right here is going to be your acid or carboxylic acid, you can say. So let's just see what we got. I mean, obviously in ester and carboxylic acid, you do have these carbonyl groups. The acetyl bond O is also called carbonyl. It's not really a function group, but it's just the name of this thing, the carbonyl. And you do have aromatic carboxylic acid, esters, carbonyl, so that leaves you with an alcohol. What students really going to do is, as soon as they see an OH there, it's going to come in their mind that they got an alcohol, but that's not really an alcohol. That OH is actually a part of the acid. A student add a solute into water. After a few minutes, she noticed that all salt has been dissolved and the resulting solution has cooled down a few degrees. So when the dissolution of the salt took place, maybe it absorbed some energy and it took the energy from the surroundings, which in this case is going to be the solution, and that what made that solution cooled down. So that's how you want to think of it. Um, so dissolution is an endothermic process if the solution has cooled down a few degrees. So that leaves you with the C and D only. You can rule out A and you can rule out B because they say it's exothermics there. But then typically if it's an endothermic and if it does happen on its own, there must be something else that making this reaction or this dissolution process spontaneous. Now, when you're dissolving a salt, what's happening to the entropy? Now, salt, when it's a solid, is just an NaCl or KCl or whatever. But when it get dissolved, it's broken into ions. So typically, your entropy is going to be increasing because you have like in a solid before, and now everything is dissolved. They are more freely to move around. So your entropy is the one that's going to be increased here, and that's going to be the one that's helping the salt to dissolve, even though it's an endothermic reaction overall. So this is going to be in a D as an answer option. Okay, let's look at this second section here, which the first question says, how would the rate of the given reaction change if the concentration of A is tripled, B is doubled, and C is halved? So the rate expression is given right here. Now, C is irrelevant because it's in a zero order with respect to the C, so I don't really have to worry about that. But when I'm looking at A, so A is tripled, so I can write down 3A, and then B is doubled, so I can write down 2b to the power 2. So when I do the math here, that's going to be 3 coming from here. And then 2 square, so that's going to be 4. So that's going to be 12. And then the A and B kind of stays as it is because that's your reference from the beginning rate law. So it should go up by a factor of 12. So that's how you really want to look at this question here. Which of the following statement is not correct? Delta G of a spontaneous reaction is negative. Well, it is negative, right? So that is actually correct. The positive value of E of the cell or E0 of the cell reflects a spontaneous value. Well, if you can create a voltage, a battery with a voltage of positive at the end of the day, that is going to be spontaneous. So that's correct as well. Delta G non-standard of an equilibrium reaction is 0. That's also correct. And galvanic cells are not spontaneous. Ew. The galvanic cells are also called the voltaic cell or the spontaneous cells. They are the one that we use in the batteries, like the remote battery, cell phone batteries, as long as you're not charging it. When you start charging it, then it becomes electrolytic cell, but when you're just using it on its own, they are typically spontaneous. Those are your galvanic and voltaic cells. So this is actually going to be D. Electrolytic cells are non-spontaneous, so that's also correct. Which of the following is not true about the voltaic cells? So remember, the voltaic cells are the one that are actually the spontaneous or the galvanic cells. That's another name for it. So in voltaic cells, you have to kind of picture out how does the voltaic cell really work. You have the anode, you got the cathode. At the anode, the oxidation takes place. So remember the A kind of goes together with the O. So that's correct. Electron flow. So if you have an oxidation being taken place at anode or the anode half cell or oxidation half cell, then the electron must proceed from the oxidation half cell to the reduction half cell. So that's also true. Um, when you lose electrons on the anode, so typically, let's say you have a metal on the anode electrode, so it loses electrons, so it becomes maybe M plus 1 and 1 electron. So this is an electron that's transferred onto the cathode or the reduction half cell. But then this electrode itself is losing its mass because it's converting into an M plus, which goes into the solution. So over time, the mass of the anode electrode goes down, or the oxidation half cell electrode goes down. And but on the other hand, what happens at the reduction half cell? So you have some other metal, so I can just call that to be N, and maybe it's N plus in the solution. It gains that electron that's coming from the oxidation half cell and makes the N solid. So this N, or this metal at the anode, or at the cathode rather, get deposited onto the electrode, so it actually gains the mass. So remember, your anode is the one that actually loses the mass, and the cathode is the one that actually gains the mass. So it seems like that's going to be an incorrect statement. So we'll just kind of put that right here. But let's just see what's happening with the rest of these guys. The cations from the salt bridge travels to the reduction half cells to prevent excessive buildup of negative charge. Now, I just said that, okay, we have um, the N plus gaining that electron, making the solid. So whatever the counter anion you're going to have with the N plus here is actually going to be left in the solution for the reduction half cell. So it actually starts building up an excessive negative charge. And to take care of that negative charge, you must have the cation from the salt bridge coming to balance that out. Because remember, the solutions of your oxidation and reduction half cells is typically like, in the sulfate forms. Like if you look at zinc and copper cell, you would have zinc sulfate and copper sulfate. So if you take copper 2 plus and make the copper solid, that leaves it behind with sulfate. So that's a lot of negative charge left behind. So that's also true. The voltaic cells have a positive E0 of the cell. We just talked about that. The galvanic cells are the same as the voltaic cells or the spontaneous cells. So that leaves you with a C as an answer option. Radioisotope I-131 is used in imaging of thyroid glands and in treating thyroid cancer. The half cells of iodine-131 is approximate 8 days. How much iodine-131 would remain after 24 days if the original amount is 50 grams. So remember, all these decays follows first order kinetics, where you can simply say, okay, if the half-life is 8 days, the total time I have is 24 days. So that means I'm going through 3 half-lives. That's the first thing you want to figure out, how many half-lives it's going through. So if I'm going through 3 half-lives, and if I'm starting out with 15 milligrams, so in the first half-life, it will drop down to 25 milligram. And then in the second half-life, it will drop down to 12.5 milligram. So that's your one, that's your two. You're doing a total of three half-lives. So in the third half-life, it will be 6.25 milligram. So that's going to be a third half-life there. So that's going to be your D in there. On 25, asking, consider the following standard reduction potential values. Students asked to construct a battery to produce a maximum EMF from the following half cells, and calculate the half cells. So you have to actually figure out what half cells you want to use and then eventually figure out what's going to be their EMF. So typically you want to go with two reduction potential values here, the one that's going to be the lowest and the one that's going to be the highest. So the highest in this case is the first one, and the lowest in this case is actually the third one. So I want to make sure I do reduction with this. I want to make sure I do oxidation with the aluminum. So when I'm doing the reduction, it would still stay zero point 0.8, and when I'm doing the oxidation, I would have to flip it. So typically it's going to look something like this. So you have Ag 1 plus 1 electron going on to make Ag solid, and then the E of that is going to be 0.80. When I'm looking at designing the oxidation half cell, I'm picking the one that's going to be giving you your lowest reduction potential value, because when you flip it, it's going to have the highest oxidation potential value. So when I flip this third one, it's going to make aluminum solid, and it's going to get broken down into 3 electrons plus aluminum 3 plus, and its oxidation half cell is going to be 1.66, and eventually you're going to have to add them up. But before you add them up, you're going to make sure the electrons are same on the oxidation and reduction. So you would have to multiply this by 3, the first one. But remember, whenever you multiply the reduction half cells by a number, your reduction potential values does not change. So at the end of the day, you have created the cell here, the battery here, with the oxidation and reduction half cells there, and then you're going to add up this 1.66 with zero point 0.8, and that will give you the EMF of the battery. So that's going to be 6. 8 plus 6 is 14, and that's 2.46. Which of the following statement is correct about RNA and DNA? RNA and DNA but contain same, well, not really, because that's really the difference between those two. Well, one of the difference between those two. RNA is a deoxyribose, and well, DNA is a deoxyribose, and RNA is a ribose. So there isn't a difference of an OH presence in the sugar molecule there. RNA is a double standard polymer. DNA is, well, that's literally the opposite. DNA is a double standard. Most of the RNAs are your single standard. RNA contains uracil, and the DNA contains thymine as one of their nitrogen bases. Well, that is actually true. The thymine is not present in RNAs. Both RNA and DNA serves the same function in human. No, that's not really true. And then E is not going to be correct either. So that leaves you with C there. Okay, let's look at this reaction diagram here. So before we do anything, just figure out what's really going on. We have one energy hump, second, third, so that's 3 steps there. B and C are going to be your intermediates here. So you got 2 intermediates, 3 steps. A and D are your reactant and product. When you look at their relative positions, D, your product's at a higher energy than the reactant. So this is actually going to be, you call that as an endothermic, depending on what you have on the y-axis, or you can call that as an endergonic if you have it in delta G. So let's just look at the answer options now. The reaction takes place in 2 elementary steps. No, we just said it's got 3 steps, so that's incorrect. The first elementary step is the rate determining. Well, to determine the rate determining step, you're going to have to look at their activation energies. When you look at the second step, that actually has a very high activation energy compared to the rest of these steps. So that is not going to be correct either. The overall reaction is not spontaneous. Well, we did say it's an endergonic, which is the same way of saying non-spontaneous. So that seems to be correct so far. Addition of catalyst will lower the position of A and D. Well, whenever you add the catalyst, it lowers the activation energies, but it doesn't really change the positions of your reactants and products and even the intermediates. So when you add the catalyst, your energy profile diagrams may change to something like this. But it's not really relatively changing the positions of your reactants and products and even the intermediates. There are four high energy activated complex and two intermediates. Well, we did say there are two intermediates, but as for your activated complex go, that really depended on the steps. So if you have three steps, you actually going to have only three activated complex there. So that leaves you with C as your answer option only there. Okay, which of the following aqueous solution would decrease the freezing point of the water to the lowest degree Celsius? That's one of the colligative properties, and remember in the colligative properties, all it really worries about is how many ions or how many moles you really have, technically. So figure out what the Van Hoff factor is going to be theoretically. So NaCl breaks down into two ions, MgCl2 breaks down into three ions, AlCl3 breaks down into four ions. This breaks down into two here. HCl breaks down to two. But then in addition to that, you also got to figure out what's really going to be the moles of ions at the end of the day. So this is going to be 50, so it's going to be 0.05 times 3 times 2 when you're just multiplying all together to find the moles and then eventually the ions moles. So that's going to be 6 times 5, that's 30, that's going to be 0.03 moles of ions there. When you look at this second one here, so it's going to be 0.04 times 2 times 2, so that's going to be, oh, times 3 rather. So 3 times 2, that's 6, times 4, that's 24, so that's going to be actually 0.024, so that's literally less than what we have on the A. 40 milliliters, so that's going to be 0.04 times 2 times 4. So that's going to be 8 times 4, that's 32, so that's 0.032. So far I have the greatest here. And then I got 40, so 0.04 times 3 times 2. So how much is that going to be? 6 times 4 is 24 again, so that's going to be 0.024. That's the same as B. And this last one here, I've got 0.07 times 1 times 2. That's just going to be 14, so 0.014. So that's going to be the lowest actually. So whichever actually gives you the highest ions or highest moles of ions, or eventually the number of ions, that is going to be the best to decrease the freezing point, because that's what you really worry about in colligative properties, whoever gives you the most number of molecules or ions. So that is actually going to be C as your answer option there. Identify the correct IUPAC name for this molecule. Now you have to look at what you really got going on. It's in a ring, so you can start anywhere in terms of numbering. You have an butyl group there, you got a chloro here, you got a bromo there. They're all have an equal priorities in terms of their, because they're all substituents. And to get that right, I want to make sure they all get the lowest number possible. And for them to get the lowest number possible, all of them, I would have to start it right here. So that would be 1, 2, 3, 4, 5, 6, and 7. This is the only way where they can all get the lowest number possible. If you start counting from this side, that's 1, 2, 3, 4, and 5. That would also give you the same numbering system, but then um, in that case, you want to have to go with an alphabetical order. So when I'm comparing this group and this group right there, your chloro, that starts with C, and this is a third butyl group. The third doesn't count in the alphabetical order. It's the B that counts in the alphabetical order. So B comes before C. So that's why you have to start it from here. So you want to make sure you know the rules on naming the IUPAC names there. Now I want to put that in the alphabetical order. So bromine comes first, so that's going to be 5-bromo, and B has 5-bromo, D has 5-bromo, and you can just ignore the rest, seems like here. And then after that, between 1 and 2, I would have to have third butyl comes first before the chloro because B comes before the C. So it's going to be 5-bromo, 1 third butyl, 2 chloro, cycloheptane. So that is going to be really the answer for this one, B. Which one of them is nucleophilic Well, nucleophile means you have to have a lone pair of electrons. You got two lone pairs of electrons on this oxygen. You have three here. You have two on this sulfur here. This BH3 does not have any lone pair of electrons. Remember, the BH3 has an incomplete octet. E also has a lone pair of electrons on the nitrogen. The BH3 itself is actually act as an Lewis acid. So the Lewis acids are also called the electrophiles. So they're not really the nucleophiles. So that's going to be the least nucleophilic in that case. A student is asked to perform two separate reactions of one butanol with PCC and KMNO4. Both of those are actually oxidizing agent. So upon proper workup, the PCC is an oxidizing agent that actually stops the reaction at an aldehyde, and KMNO4 takes the reaction all the way to a carboxylic acid. So what you're really going to be making out of PCC and KMNO4 is an aldehyde and an acid. So the only answer option that has those is your A. Arrange the following in order of increasing acidic strength. So when you're looking at acidic strength, first focus on their functional groups. When I'm looking at their functional groups, um, 1, 3, and 4, they all have carboxylic acids. 2 is an alcohol. So alcohol is indeed going to be less acidic than the rest of these guys because those are the acidic acids or the carboxylic acids itself. So 2 should be the lowest. So I should have either B or C as your answer options. One of those two. A is out of the question. D is out of the question. So that leaves you with the other thing. Then when you're looking at 3 and 4, you have this NO2. NO2 is actually an electron withdrawing group, and CH3 is an electron donating groups. Electron withdrawing groups makes acid stronger because they can stabilize the conjugate base. So 4 should be the strongest acid. 3 should be weaker than even 1 because the 1 is kind of reference. There's really nothing going on 1. So 1 should be in a stronger acid than your 3 because electron donating groups makes acid weaker. Electron donating groups are actually better for the bases but not for the acids. So 4 should be the first one as the strongest. So here, and then after that in the line should be 1. So we got 1 right there. So it has to be C. Okay, this question 30 to 40 are partially based on this information provided in the passage below. So you have to actually read the passage, kind of get some information, and use that information to solve the problems. And this is what I tell students to kind of highlight some of the information that's going to be you think is going to be useful, and let's just kind of go through it. It says extraction and recrystallization are the two of the most common techniques used to purify organic compounds, organic products from the reaction mixtures. Usually extraction is carried out directly on the reaction mixtures containing final products along with the impurities in organic salts and other side materials, followed by the recrystallization and chromatography. Well, so far just an introductory stuff. I don't really see anything significant that I can use. The natural and synthetic organic compounds follows the principle of like dissolves like. Well, that's something important. So I want to make sure I highlight that. And express the high solubility in either polar, so polar solvents that you're given here, ethyl acetate, ether, dichloromethane, and chloroform, and or nonpolar. So nonpolars are hexane, gasoline, other hydrocarbons, organic solvents. So depending on, if you're dealing with a polar compound, it will dissolve in polar solvents, and if you're dealing with a nonpolar compound, it will dissolve in nonpolar solvents. Organic compounds containing 6 or more carbon atoms typically um, are seldom soluble in water unless highly polar groups are present. So that's an important thing to do. Like they are usually insoluble, but sometimes they give you an information there says except or unless. That means there is a good chance they're probably going to be asking you questions based on that. So they are going to be insoluble in water unless they have a lot of polar grips present on them. So maybe something I want to make sure I highlighted. However, these compounds can be made soluble in water. Well, they're talking about back to those compounds that were not soluble. If you can make those soluble if they have any acidic or basic function groups. To illustrate how it works, let's look at the isolation of cocaine. This structure is given right here. That's the structure of cocaine. All right, so when I'm looking at the structure of cocaine, the first thing I really kind of look at is actually this nitrogen atom. So that's actually going to be your base. So it does have a basic properties in there. Um, from the coca leaves. The cocaine is a Schedule II drugs under the Controlled Substance Act and has a high potential for abuse and dependency. So make sure you guys don't want to abuse that. In a few countries, however, it also serves a medical purpose and primarily used as a topical anesthetic for the upper respiratory tract. Okay, that's just an aside information we got. This is a general representation of two phases. When you have, thinking of mixing water with gasoline or oil, they don't really mix well one another, and they separate out, make two layers, and you have to worry about what's going to be on the top, what's going to be on the bottom, and that actually really depends on the density. So that's something that you should know already since you're taking a lot of chemistry stuff, but it may tell you somewhere in the paragraph as well. The coca leaves are soaked in nonpolar solvents such as gasoline and hexanes to extract all the nonpolar molecules along with the neutral cocaine. So this cocaine itself is actually very nonpolar. It's got a lot of hydrocarbons, just carbon-hydrogen bonds. It does have this nitrogen and a little bit of an oxygen, but these are overshadowed by the rest of this molecule because it's so hydrophobic. So it would be you can dissolve that in nonpolar solvents. But if water is added to phases, organic, that's going to be the top in this case, and the aqueous layers are formed as shown in figure 2, the actual position of the organic phase is dependent on the relative density. So this is where they talk about the relative densities. The denser liquid stays on the bottom. So whichever is more dense is going to be on the bottom. So that's an important information to know. Neutral cocaine is only soluble in organic solvents, but can be pushed into the aqueous layer by protonating its basic functional group by treating with a strong acid, as shown below in the scheme. So we know this is going to be more dissolved in the organic. That's what the paragraph is saying. But I can protonate this nitrogen and have this charged cocaine here, and now this is going to be more soluble in water. So you can push that into an aqueous layer. Okay. Similarly, you can have an organic compound with acidic functional groups that can be made soluble in water by extracting with basic water such as aqueous NaOH or NaHCO3. Charged compounds shows high solubility in water, so you can have up to roughly 20 carbons and only one charge on them that would still be dissolved in water. So this so far what information we got is how you can make a particular compound go in and out of the water layer or aqueous layer from your organic layer by using the properties of acid and base. And then also where the position is going to be. So that's an important information that you have. Okay, it says your teacher divided your class in 4 groups of 3 students, each asked to perform a different set of experiments. 3 compounds A, B, C are shown. Okay, so 3 compounds here are shown. Just be able to identify those. You got an acidic function group here. You got a basic function group here. And this is just neutral. There's really nothing else on there. No function groups on there. Um, it's safe to assume that all these compounds are in their neutral form, and in this form, all of those are soluble in the organic solvents that are listed, and they are insoluble in water. So all those compounds will be insoluble in water when they're in their neutral form, but they would dissolve in any of those solvents that are listed on this side here, along with the density. So anytime you have an information in the table, there's a good chance you're going to be using that to answer a question. Group 1 students dissolves 3 compounds in dichloromethane. So remember the dichloromethane has a density of 1.3, and added equal amount of aqueous solution of HCl. So your solution of HCl or water, that's going to have a density of 1. So that means your dichloromethane is actually going to be on the bottom. So that's the information you want to take that away. And your aqueous layer is going to be the top layer here. After shaking it well, student observed the formation of 2 layers. So your HCl is actually going to react with toluidine here because it's got the basic. So once it gets protonated, that would be in your aqueous layer. So if someone asks you what's going to be in the aqueous layer, that should be B. And what's going to be in your organic layer, that should be your A and C. So that's so far that's the information we have. Group 2 students added a mixture of 3 compounds in the water, forms a cloudy mixture. Students then added multiple pallets of sodium hydroxide, which is the base, and estimated the pH of the solution by using pH paper. Student observed that the number of precipitates originally present has been decreased. Well, when he added sodium hydroxide, what's going to happen? The sodium hydroxide will react with this acid and it would make that benzoate dissolve in water, but the rest of the 2 compounds will not dissolve in water. So that's why your precipitates has been decreased. So you can say the A would dissolve in this case, but then B and C would stay insoluble. So that's the information that you want to get out before you actually start looking at the questions. This set of students decided to dissolve the mixture of a diethyl mixture of compounds in diethyl ether. Student then added the aqueous solution of NaOH. After shaking it well, student observed 2 layers and no precipitate. So when you add NaOH, it's going to again react with the benzoic acid, not with the toluidine and naphthalene. The naphthalene would not react with any of the acid and bases to begin with. But diethyl ether, let's look at their densities. It's 0.71. So diethyl ether should be the top layer in this case, and your aqueous layer is going to be the bottom. So what should we have in the aqueous layer? Since it's reacting with the NaOH, it's going to deprotonate the benzoic acid, and that would be a negative charge. So that would push it into the aqueous layer. So A should be there in the deprotonated form, and on the top layer you should have B and C technically, both of those there. Students in this group were given an organic layer from 1. So organic layer from 1 had an A and C. So that's what we have so far. It was extracted with an equal amount of NaOH. So we had an A and C. So A was acidic. So now we're adding NaOH. So that means that's going to push this into the aqueous layer. So the aqueous layer would have an A now, and then your organic layer would still have the C. Then they were collected in different beakers. Concentrated HCl was added in the aqueous layer until it precipitates form. Well, remember this A is in a deprotonated form, so it dissolved in water. But when you add HCl to it, it's gonna become protonated, and then it's gonna crash out in the water layer. And then the dichloromethane from the organic was evaporated, and the white solid remained. So obviously that is going to be your compound C in that case. Okay, let's look at the question now. How many sp2 hybrid carbons are present in the structure of cocaine? Well, that question does not have anything to do with all this information given in the paragraphs other than just the structure of cocaine itself. So when you go back and look at the structure of cocaine here, we see how many sp2 carbons I have. I got 1 right here, got 1 right there, 2, that's 3, 4, 5, 6, 7, and 8. I don't really see any other sp2 carbons here. So that's going to be 8 carbons for this one. What compounds will be present in the bottom layer of group 1 student? So this is why you actually have to decode the information that's already given in the passage, so that when you go back, it's easy to um, find the answer. So it's talking about the bottom layer of group 1 student, and we said the bottom layer was this right there. All right, and that bottom layer contained A and C. We already had that answered out, and that's literally what they were asking for. So it's going to be A and C in this particular case. That's going to be on the bottom layer, which is the dichloromethane. In group 2 experiment, what compound stayed insoluble throughout the procedure? So what really happened in group 2? We dissolved that in water, cloudy mixture formed, and then we added some sodium hydroxide. So sodium hydroxide made the benzoate or benzoic acid dissolve, and then B and C stayed insoluble. That's what we had already retrieved in the information. So that means your B and C should have stayed insoluble throughout the procedure for this particular one. What compounds were left when the dichloromethane was evaporated by group 4 students as described in the procedure? Well, I think we already answered that as well. So we said dichloromethane from the organic layer was evaporated and white solid remains, and we said that was actually C in there. So that's going to be C. So if you have decoded the information from the paragraph, it's going to be easy to get the answer out when you do the questions. What compounds would be present at the top layer of group 3 experiments? On the top layer on group 3, so on the bottom we said it was A, and on the top layer, which was the organic, and we had B and C in there. Okay, so that's going to be just B and C. That's it. Let's say the molecular formula of table sugar, that's the sugar that we eat. Its Howard structures is shown below. We know sugar dissolve in water, all right? So if you say that it's insoluble in water, that's going to be incorrect. This is just a real life experience. It's soluble in water because it makes dispersion forces only. Well, if it makes dispersion forces only, it cannot be soluble in water because water is very polar, so it has to be making a hydrogen bonds with the other guys. It's insoluble in water. That's incorrect as well. It's soluble in water because it contains multiple alcohol groups that can make only dipole-dipole interactions with water. Well, since you have an OH groups on them, they all are going to be capable of making hydrogen bonds, so that's not going to be correct either. E says it's soluble in water because it contains multiple alcohol groups that contains excessive hydrogen bonds that can make excessive hydrogen bonds with water. That's true, actually. And that's one of the information that was actually given in the paragraph. I don't know if you guys paid attention to it or not. It did say that typically your organic compounds with 6 carbons or more are seldom soluble in water unless many highly polar groups are present. And that's exactly what we got going on here. We have a lot of polar groups present in there. How many sigma and pi bonds are present in p-toluidine there? So p-toluidine is this guy right there. I'm just going to erase that. So remember your sigma bonds, your pi bonds are the double bonds. So that's 1, 2, 3. So you only have 3 pi bonds there. So that's easy enough. So I can come down here and I can be like, it could be either this one. That's not the answer. That's not the answer because the pi bonds comes on the second line. That's not the answer. So it's either A or D or E. So let's count the sigma bonds now. I have 2 hydrogens here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I got hydrogens here, that's 10, 11, 12, 13, 14. And then this also gonna have 3 hydrogens, this carbon, 15, 16, and 17. So I got 17 sigma bonds there. So it has to be an E. The last thing, if paratoluidine is reacted with bromine in the presence of iron 3 bromide to perform an electrophilic aromatic substitution, what would be the most likely product? So again, this question is indeed using the structure of paratoluidine, but it's not, doesn't really have any information on the electrophilic aromatic substitution. So that's something you have to know or you have to do based on your knowledge. And remember, the bromine can be installed on the ortho para positions with respect to the electron donating groups. So when I'm looking at the paratoluidine here, for example, the NH2 is a very strong activator. So since it's a very strong activator, it can put bromine on its ortho and on its para position. So it can do actually multiple substitutions there. And since the pair position is already taken, I'm not going to be able to put any bromine there, but I can certainly put the bromine on the 2 respective ortho positions with respect to the NH2 there, so here and here. So that leaves you with this answer option C here, or E here rather, because you got 2 bromines here.